Hello, my name is Dr. Ephraim. Today I will be discussing integration by substitution, which is commonly known as u-substitution. And so in this lesson, I'll briefly talk about the idea behind u-substitution, the mathematics behind u-substitution very briefly, and then I'll work out two examples, basic examples, good examples. So let me start by letting h of x be a function which is a chain of two functions, f of g of x. So if I differentiate h, the chain rule tells me to take the derivative of the outside function times the derivative of the inside function. So h prime of x is the derivative of h of x. So this expression is the derivative of that expression, f of g of x. So since h prime of x is the derivative of h of x, then h of x is antiderivative of h prime of x, or f of g of x is antiderivative of f prime of g of x times g prime of x. So I can rewrite that as the integral of f prime of g of x times g prime of x dx is f of g of x plus c. So what is going on here? So what's going on here is this. If I let u be g of x, if I rename this expression g of x by u, then this becomes the differential du. The derivative of u is g prime of x, so the differential du is g prime of x dx. So this whole thing becomes the integral of f prime of u du. Well, the integral of f prime of u is f of u plus c. But what was u? U was g of x. So this becomes f of g of x plus c as expected. Okay? So if I see a chain of two functions and I see the derivative of the inside function sitting by dx, then this u-substitution, letting u being g of x, is a good tool to integrate this expression. Okay, so let's have a couple of examples here. So my first example is the integral of sine of x squared plus 5 times 2x dx. So as you can see, this is a composition of two functions, sine and x squared plus 5, x squared plus 5 being the inside function. So if I differentiate x squared plus 5, I get 2x. So this looks very much like that expression here. The derivative outside sitting by dx, and this is a chain of two functions, f prime of g of x. So I'm going to let u be the inside function x squared plus 5. Well, what does that mean? Then if you differentiate u with respect to x, that gives you 2x. In other words, du is 2x dx. At this point, I always like to solve for dx. So if you solve for dx, that gives you du. Let me write this up there. So what did we get? We get du equals 2x dx. So if you solve for dx, then this gives you du over 2x. So I have u equals x squared plus 5, and dx is du over 2x. Well, some people like to use this as du and put it in here right away. This being a simple example, that's possible, but to make a pattern, I always solve for dx, and that's what I will do now. So what do I have here? I have u is x squared plus 5. These are the two things that I need for my integration, and I have dx solved for, and I have dx is du over 2x. So this expression, my original integral, now becomes sine of x squared plus 5 times 2x dx becomes the integral of sine of u because x squared plus 5 is u, and 2x is there, but dx is du over 2x. dx is du over 2x. And as you can see here, I have a 2x and I have a 2x. I can cancel them out. That will give me the integral of sine of u du, which easily is the negative of cosine of u plus c. But what was u again? U was x squared plus 5. So that gives me negative of cosine of x squared plus 5 plus c. And that is the integral of my original expression. Okay, let me do another example. And this will explain why I like to solve for dx instead of just putting du in to my expression. So my second example is the integral of x squared times cosine of x cubed minus 2 dx. Here I have a chain of two functions, cosine of x cubed minus 2. The inside function is x cubed minus 2. If you differentiate x cubed minus 2, you get 3 times x squared. And I don't see 3 times x squared sitting next to dx in here. But however, I have an x squared. So the only thing missing is the constant 3. So missing a constant will not be a problem when you apply the substitution technique. So we can work with a constant multiple with no problem. So let's let u be x cubed minus 2. Then du becomes 3x squared dx, and solving for dx, that gives you du over 3x squared. Now, okay, these are the two things I need. I need u equals x cubed minus 2, and dx is du over 3x squared. So my original expression now becomes, well, what is it? It is x squared cosine of x cubed minus 2 dx now becomes the integral of x squared cosine of x cubed minus 2 is u, dx is du over 3x squared. And now we can see that the x squareds can cancel. That will leave us with cosine of u, the integral of cosine of u over 3 times du, or this 1/3 is a constant, so you can pull it out. 1/3 of the integral of cosine of u du. Now let's integrate cosine of u. Well, we know that the integral of cosine of u is sine of u. So that gives us sine of u plus c. Well, what was u? u was x cubed minus 2. So that gives us 1/3 of sine of x cubed minus 2 plus c. And that's the final answer. So I like to point out a couple of things in here. One is that when you see a chain of two functions and you see the inside function, its derivative outside by dx or a constant multiple of the derivative. Constant multiple of the derivative is good enough. In this case, the derivative would be 3x squared, but this is the 3 is missing. So that should be okay, and this u-substitution is a good technique to apply for a function like this. The second important point that I like to point out is once we make our substitutions in here, so we have our u's calculated and dx calculated, and once we make our substitutions and the x's cancel out, we should get an integral, completely integral of the expression u, and we shouldn't see an x in here. All right, I hope this helps. Thank you and goodbye.